And share my screen. Cool. So can everyone see my screen?
Yes.
Nice. So today's paper is called "On the Existence of Universal Lottery Tickets." And I'm not actually going to go into the abstract. I want to actually start with like what is a lottery ticket, and they describe a lot of the concepts that we're working with here in this paragraph, the second paragraph of the introduction. And so there's this paper from 2019, and it says it provided a proof of concept that sparse neural network architectures are well trainable if initialized appropriately. And they call their proof the lottery ticket hypothesis, and states that a randomly initialized network contains a small subnetwork that can compete with the performance of the original network when trained in isolation. So actually, I think that a nuance here is when they say a randomly initialized network, often they mean a randomly initialized network that's been trained. Often, like even in the experiments, what they'll do is they'll train a network and then they'll try to find that subnetwork within it to, which they call the lottery ticket, which is a sparser network. And where's the motivation?
Wouldn't that be against the trained in isolation? And when it says trained in isolation, it sounds you train only the sub network. It should work.
Well, yeah. So, but the idea is that you have the initialized network, and then train, and then you take out a much sparser network from it, and you train it, and you get like a very sparse or much smaller network that works well. And the motivation for it is in the first paragraph, which is that. So they're saying that deep learning comes at has had major breakthroughs, but it comes at considerable computational cost, and that in general, like the trend has been towards wider and deeper networks, but reducing the size of networks before training can be really like it can reduce the amount of training time, the amount of and consequently like the amount of compute and cost of training networks. And then also sparser networks are smaller, which means that they can fit on like smaller devices and then be deployed in more places. So it could increase their use and impact. And one key thing to note is that the only reason why they can claim the reduction in reducing the size of networks before training is the concept of universality that they're talking about later, which is that they can identify these universal subnetworks. Anyway, and so again, a lottery ticket is a sparse, small subnetwork that is like found from a larger network that's through pruning. And then there's a paper in 2020 where they conjectured that the existence of strong lottery tickets, which do not need any further training and achieve competitive performance at their initial parameters. So essentially that means that you could take a network that performs pretty well and is trained and is very large and just like sample or prune its parameters to get the much smaller network. And then let's see, these tickets could thus be obtained by pruning a large randomly initialized deep neural network. Unfortunately, existing pruning algorithms that search for strong lottery tickets have high computational demand. And so this is where they talk about the concept of universality, which is universal lottery tickets that once identified can be effectively reused across a variety of settings. Okay, so we won't go through that. Let's talk about what they mean by universal lottery tickets. So again, I'm just going to say it a lot because to me it was a very unique and unintuitive concept. A lottery ticket is you take a very large network that's got randomly initialized weights, and then you train it, and then you prune it to get like a much sparser network. And okay, where's the universality definition? Oh, universal. Okay, it's all the way to find universality here. Okay, well, actually, sorry, let's look at the mathematical notation for what a lottery ticket is first, because that's kind of important. Okay, so when you're defining a lottery ticket, you can ignore this up here for now. What it is it's you have a large, usually untrained deep neural network F naught, which we call the mother network, a smaller target network F, which is like your really sparse network that you want, and a close approximation, our lottery ticket F epsilon, which corresponds to a subnetwork of F naught. F epsilon is obtained by proving F naught as indicated by a binary mask that specifies for each parameter whether it's there or not. So yeah, here they say usually untrained deep neural network. I'll go back to this. I don't know if anyone has any. I literally think that they say usually untrained, but it seems like a lot of the times it's trained or it's not very clear to me. Anyway, we'll come back to that. And so again, you're trying to prune from this this network. And so now they have this, here they define what they call universality, which is like, let there be a function, a family of functions F, which map from S, which is some like subset of RD, where R is real numbers and D is the dimensionality of your input features. So like if you have a 32 by 32 image that's your input, then D would be 32 times 32. And then it goes to Rn, so in most cases n would be 1, but it could be anything. Like for example, in their case, all their proofs focus on linear regression. So you're outputting to like, you could be just predicting a property of like an object, like its length, or you could be predicting multiple continuous properties of the object. And so their concept of universality is that you get this function b, and you in this case from your larger mother network, and so b would be F epsilon. And what you can do is you can actually use it to model any of the functions in this family F by adding on a linear layer to that function b, or that network F epsilon, and you'll always have to be within some error of the correct function. Does that make sense? It's like you have a network which goes from your input features to some like hidden dimension k. So like maybe you went from 32 by 32 features to 128 features, and then you can just multiply it by some matrix that you train afterwards plus a bias, and you'll be able to approximate a family of functions. And yeah,
that is quite a. It's actually not that crazy if you think about it.
Yeah.
Because if you take a case where the input dimension is 1, right? So then, and the output dimension is 1, then you're asking, can I approximate any function out of a class of functions with a linear combination of representation functions?
Mm-hmm.
And that is essentially what Fourier analysis is, right? So you can prove that any function that is, I think, L2 normalizable can be approximated. So the question is now, does it extend to higher orders?
Mm-hmm.
So what is B?
So B is, here they're defining universality, but B would be F epsilon. So the network that you pruned from the larger network.
It could be any.
But in this definition, it could be any function.
It could be any basis representation of your.
Which is, yeah, so it makes sense. I don't understand the concept, because if B and F can be anything, and there is a linear combination, the linear multiply B with the matrix and gets F. C is a vector too, right?
No, what it's saying is that you can model any function in the family F, so any G, by just taking B and adding a linear layer on top of it, or like a linear transformation on top of it.
So technically you would, the only thing you need to train is the linear layer, right? Which is,
Yeah.
And at this stage, we haven't said what E is. Like we just say that it will be smaller than E, but we don't know the size of E.
Yeah.
I mean, that makes sense, right? If S could potentially be quite large, right? So you know there are always going to be some boundary effects. And but as long as the function is sufficiently smooth or whatever, you can always show that there's the error can be bound in functional analysis. Yeah.
And
So does it,
sorry, go ahead.
I was saying, so is it practically, I guess I'm just thinking in terms of like applications. So you could have the case you mentioned, like a image classification.
Mhm.
And then if you say you find B and then you go to a different task, is it constrained on like what? So let's say a different task, like an NLP task where you have embeddings that are the same size as D, and you're trying to classify something there. Then does that apply?
I actually don't think so. Like the one nuance to me of this whole thing is that B is like a fixed transformation after the network is done. And Arvid's description of it as a set of basis functions is really good. That's actually what they use throughout the paper to describe, like, to show, they basically, all their proofs are that B can approximate basis functions, which can approximate any function. And so that means that you learn a fixed set of basis functions, which means that you can only use, like, the family of functions F can, in my opinion, can only be like, they have to actually require the same basis function, so the tasks have to be pretty similar.
Also, it says for every F, there exists W and C. You can choose the W and C for every F and then optimize over X. No, not optimize, the worst case over F.
Well, you
Or
can't,
W, right?
Over X, worst case over X, right? It's saying that the farthest distance over after the linear transformation from F is bounded by some constant.
so what I'm saying is that, I think you're quite limited in what your family F is. It's not like you can take a network found for an image classification task and use it in NLP here. I think those functions are sufficiently different that they couldn't be within the same family, and like you couldn't find but like,
That would be because the input dimensions would be widely mismatched. Right?
well, if say they were the same somehow.
So if you have like a vocabulary of 728 words versus like a picture of images, right? Well, then I would think not, right? Because the restrictions on the function family must be they are like at least continuous or something, or digits, right? So otherwise you could always imagine like you have a function that is smooth except for a single point where it has an arbitrary value, right? In that case, the supremum could be in principle arbitrary large. But I think if the moment you make the function smooth, then the chance of hitting such a supremum is essentially zero because it's bound by the Lipschitz method. So I think there's a lot of depth in the assumption of what the family of function is, but because of the definition, it's fine because the definition is the definition.
Yeah.
But it doesn't say anything about the error, like how big the error can be, and it doesn't say what relates K, the number of basis functions here, to the size of the error. So if you have like a flat line and then 1 point delta spike, like that's still an error, finite error.
I think the important part is X doesn't depend on anything else, the constant. I think that's the important thing, right?
The epsilon will depend.
And it's bounded, it's not infinite.
Yeah,
Okay.
but that is because epsilon will depend on S, I'm pretty sure. So the moment you would yes, I would S and the size of the input. Right? So this is a Fourier platform. Right? You can always increase your Fourier basis and therefore are guaranteed to minimize the error on any normalized function, any normalized function. So,
Yeah, and the error can go to zero as you increase k. Is that the idea?
Yes, provide, yeah, unless of course we go on the smaller subset S, I think then you can guarantee to finite, like I think on the sphere, right? So I don't actually know what the basic representation of the sphere is, but on the sphere, I think you also have an infinite number.
Okay.
Yeah.
Peter,
Mhm.
can you quickly check your email in case anyone is waiting downstairs?
Oh, yeah.
I just realized there might be.
I think the cool thing is here that they
Oh,
say
yeah. Well, it was at 12:19. I think you went down.
that was probably me, yeah.
Okay.
Okay. Cool. But again, I at least personally, I don't think you could have a network that's that universal. Maybe I'm wrong.
Well, it's-
Because it's like the basis functions and, yeah, the basis functions themselves that you learn are essentially fixed after.
yes, but the idea is that if, and I think for function analysis is right, that bases are not unique. You can always rotate your bases. And I think the crux is to say essentially, you could take any random basis because the chance for them to be collinear is so small that there must be some set of orthogonal vectors in there that allow me to spend my function space. And so probably the pruning is then to find which subset of orthogonal functions are in there. And then of course, because there's a lot of power in having this W matrix, so you can still have a lot of flexibility because you don't specify W to be beforehand. Right?
But it had, like, whatever function, it has to be a linear combination of the basis functions, right?
Yeah.
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 Oh, and this is kind of lottery ticket. So a lottery ticket is a neural network, like we said, that maps from RD to RK, where RK is like your hidden representation or like your K basis functions. And you have some mother network that goes from RD to RK as well, and you're pruning the parameters. So let's see, what are some things that I wanted to point out? Okay, so first off, all of their proofs rely on the idea that your inputs are within the interval 0 to 1. And like, but I actually think that's not an unreasonable expectation because you can just normalize or like your inputs in some way. But I do think it means that you either expect, you basically expect to only be performing interpolation with these functions at test time.
Also, if they don't have the assumption, they probably can extend the proofs to have any bounded range.
Yeah, that's
So
true,
it's just
because you
make-
can normalize your inputs.
Yeah, but it's probably just to make the proofs a bit simpler.
Yeah, it's more like to show that the function family F is restrictive enough to have like an arbitrarily small error on the finite size support.
Well, yeah, because otherwise the error would be limit bounded to the largest.
Yeah,
numbers.
if F goes really bug wild, then I think it is these things like Sobolev space, where it essentially gives bounds on the derivative of a function, which would effectively control probably the input size necessary.
And they say over here, we limit ourselves to the explicit construction of K basis functions of a family that has the universal function approximation property. So to tell you what that means, like, I think that there's proofs that you can basically take any function and within it's like within the domain of the data set or like within the domain of the function, you can approximate it with a set of polynomial basis functions. And I think the same is true with Fourier functions for periodic functions, right? Is that true? Like Fourier is for periodic functions and polynomials would be.
Well, Fourier also applies to any function. That is, they work exactly on periodic functions, probably, but you can also show that when it's like offset and everything, that the error is still sufficiently small for any function, which is
Okay.
crazy, really.
So basically, what they're saying is that you could with with, where's the statement? Oh, limit ourselves to the explicit construction of K-basis functions of a family that has the universal function approximation property is that all their proofs are based on the idea that we could take these sparse neural networks and use them to approximate either polynomials or Fourier functions, and only K of them. And because those functions have this universal function approximation property that they can approximate any function, then the sparse subnetworks or these lottery tickets can also universally approximate any function.
Is there actually a definition of what sparse means? That does it have to be like always be a fraction?
Maybe there is. I think there might be some definition of what they mean by sparsity, but they don't.
It's probably also like
I don't know where to point to in the paper for it. I think that when in the experiments they show how few parameters from the mother network they use, and it's like 2 to 5%. Yeah. So I guess sparsity is that's what they mean by sparsity. Yeah. So they basically go over two cases, which are polynomials and Fourier basis functions, and they have all this math, which is essentially saying that you can you can approximate a like a monomial, like a polynomial function using this here, this function here, and well, this is a monomial, and then you can actually express it using this over here, this function over here, so b of x, and basically their assertion is that you can approximate this function b of x here with sparse neural networks, and they can prove that you can approximate it. I think that the best way to explain it is to look at these two diagrams. So both diagrams, A is for approximating K polynomial functions, and B is for approximating K Fourier basis functions. And essentially what they do is that each of these rectangles, these blue rectangles, is a neural network. And what their point is that you can, so in the polynomial case, what you would do is you'd have a neural network for each of your D inputs. So it would be a univariate neural network, and then you would perform a convolution on those like the outputs of those neural networks. And then you would have a linear, they call it a linear neural network, but it's essentially just like one linear layer. And then you would have another set of functions, G, which is just the exponential of the inputs. And you would, those can be approximated by a neural network, and then you perform convolution on them. So essentially they're showing you like what the network architecture needs to look like, or what your search should look like from the mother network, which is you're trying to find like D sparse networks that you then perform a convolution on top of. So you need to find these D sparse networks, then you have a linear layer, which you have to find, and then you have to find K sparse networks again. And then for Fourier basis functions, you'll have a linear layer at the beginning, and then K univariate neural networks, and they're all trying to and so just to be clear, like in A, these first, like if you can see my cursor, these first blocks, they're trying to approximate this function here, but they're not explicitly using that function. They're literally using sparse neural networks to approximate it.
So where was the log applied?
They don't apply it. They're saying you can use a neural network to approximate it. And this is where a lot of their math, like their math that relies on the fact that your inputs are from 0 to 1. So they have D of those, and then up here, they're using sparse neural networks to approximate this function.
Wouldn't the exponential just get rid of the log?
I think so, yeah, that's, for some, I guess neural networks can be shown to approximate these functions within their the domain that they're showing. Because, yeah, if you just look at this equation here, you can see how you go directly from this to this. You're just taking the log. And it's like a log sum.
So this is more like for proving that it fits these common word of honor forms.
Well, so actually, so that whole theorem up here, I didn't go into it because basically what they're saying is like, yes, you can approximate functions, any univariate function with these, but like there's a lot of downsides to it. So instead, we're going to focus on polynomials and Fourier basis functions, and provide our proofs with respect to those. So yeah, they basically are saying this is what our sparse neural net, or this is what the sparse neural networks we want from our mother network. This is what they look like for the two different types of basis functions that we're using.
Did you see the question?
I don't know. That's
I don't really understand.
why approximate the log? Is it necessary because they restrict to using? Yeah, I think so. I think that they're yeah, I think it's because I guess you can show that you can approximate those functions with sparse neural network or with neural networks. That's my best guess. Without, I don't have a strong background in theoretical math, and I think I would need to know that.
Peter, is there a link between so the way you structure B? So let's say if it's not a composition of linear functions, will that break the universality condition?
So their whole the logic of their proof is that we can approximate k basis functions with these with a set of sparse neural networks, and these k basis functions are universal function approximators. So the case the sparse neural networks are, because they can approximate the basis functions, they can approximate any function. And so the B's, the way that they structured the B's, they have to be that way in order to be able to approximate the basis functions that they're talking about. Does that answer your question?
Oh, so to summarize, would that mean like only the linear combination of functions can help approximate the F given the B? Is that why?
I don't know if this is a unique way of approximating these these basic functions using neural networks, but this is the way that they're showing that you can.
Yeah, because it would make sense why they would pick particularly convolution operation, because that's linear as well, and yeah, I think there might be somewhere a link of linearity and universality here.
I think the convolution is so that you can create more complex polynomials or monomials. At least that's the one I understand better, because then you can have a monomial that's more than just a single function.
Oh, right.
I mean, just more than a single variable. So anyway, they talk about both polynomials and Fourier basis functions in this context. And then they go into basically their proofs are showing that these lottery tickets exist, which means that you can that they're within the function, and also giving you like an idea of how you have to initialize the networks in order to identify them, and basically you have to use these functions to initialize the weights of your network, and then you have to and then you can use all of this in order to, where is it? This is an existence proof. Yeah.
What is the high chance, right? So it was always the statistical argument. That
It's 1 minus delta that it exists.
So it begs the question, so once I have identified such a super lottery ticket, can can I just make a library of super lottery tickets for sufficiently generalizable functions like all the schools, and just get rid of all neural networks ever again once I have the for each dimension combination the right.
Yeah, I had my other question was actually like, okay, say that I'm wrong and you don't need to train these networks at all, then why can't you just randomly sample from those the weight initialization functions until you find the weights that you're looking for? Like what?
But that probably would take a long time, right?
But like all you're doing with if you're not training these networks at all,
Yeah.
because one element of their pruning method is they use set sum blocks. What is it called? But basically, they search through multiple layers of the network for so they're trying to find the parameters of these sparse networks, and the way they find them is by doing summing weights from different layers together to find the weight that they're looking for. But I just asked myself in that case, like, it doesn't even matter that like they're not even looking at individual layers, they're looking at multiple layers and they're adding them as a linear combination to find the weights. So yeah, for me, I was just really wondering why the mother network, if there's no training involved, needed to be a neural network and just not like sample 10,000 numbers from the weight parameters and like the weight initialization function distribution and the values.
I believe there is such a argument that says that you don't often have to even train the earlier layers of a neural network because they usually provide enough randomness to have only that later layers trained.
Yeah, well, so two things that I liked about this paper is, although it's very dense, it does say some like things that I think are worth taking note, which is like feed-forward networks of higher depth are usually more expressive, even when they have a smaller width. So like that's just something that's good to know from a practical point of view. And then the other one they say is that, which I thought was interesting and I didn't know, but maybe I should have, was, where is it? No, I highlighted it. Oh yeah, in several common initialization settings, however, the parameters of the bottom layers that correspond to the ticket change only slowly during training, if at all. So therefore, a strong ticket will often be also a weak ticket from a practical point of view. Yeah.
I'm not sure what a big ticket was actually.
Weak tickets are, I don't think they have to be, let's see. I think weakly means that you don't have, you don't train anything on top of them. You just use them directly or something like that, but they, yeah.
It sounds almost like that here they make the claim that every problem of a certain sort can be translated into regression function over a sufficiently complicated set of base parameters.
Yeah.
Cool, right? So the question is, do you still need to randomly initialize, or can you just mathematically construct them, which you do it once, and then you might be able to solve all regression and classification problems like that. It should be cool.
Yeah, like I was thinking if you're, I guess, one thing that wasn't really clear to me actually was how do they prune the network? Like what's the pruning objective that they use? Because they basically use pruning instead of training, like the back propagation to train their network. But I wasn't really clear on what the pruning objective was.
Especially when that also takes significant effort. I think they did it. So you're not saving time.
Yeah.
But then again, if I understood correctly, then once you prune it once, it should be.
Yeah, if it's universal, then you can
Yeah.
use it for a lot of different things. Yeah, so they have all these different proofs. Some are on like existence, some are on like how big the network has to be that you're fine, like how big your mother network has to be. They just provide a ton of information. That's fine. I'm not going through this because, to be honest, it's very, in my opinion, it's very dense. Great, yeah. I'll go with that. But basically, they, in terms of experiments, they did 2 experiments where like they actually knew what basis functions they wanted to approximate, and they showed that they could. And they say like after pruning 0.022, like so 2% of the original parameters remained, which is sparser than most pruning algorithms can identify. So I guess this method that they're using, the proofs that they're using, allow them to do even sparser pruning than other ones. And over here, they said they could, they kept 4% of the parameters for approximating Fourier basis functions. Yeah. This is the one that I was actually confused about whether you need to train the model or not. Oh, we train it with edge pop. Okay, so in the second type, we train our mother networks with edge pop-up, blah, blah, for 100 epochs based on SQD with momentum. Wait, there's 2 training methods here. There's the pruning method, and then there's stochastic gradient descent with momentum. And then they say parameters were normally distributed. So maybe they randomly initialized the mother network. They used edge pop-up to get the sparse networks, but then they also trained the mother network for 100 epochs in order to get like accuracy or something like that of the mother network. This is the part that really confused me about whether they train or not. But anyway, they say it finds this experiment they're trying to predict on MNIST, which is trying to predict whether an image is numbers 1 to 9. Is it 1 to 9 or 1 to 10?
0 to 1.
0 to 9. Thanks. And it finds subnetworks of the randomly initialized mother ticket architecture achieving an average accuracy of 0.95. So they have pretty high accuracy. And with polynomial architecture and 97% with Fourier architecture. Yeah. So I guess the main thing that's really interesting to me is like if from this paper, like is this concept that you don't need to train the network, that you can just randomly initialize it and then prune. And then you'll find a sufficiently good neural network from that.
You need to train the basis weights like the W. Right?
Well, the linear layer, yeah.
So that's trained, but then they're initializing the network so that the B's are not trained. Okay.
Is that also similar to this theorem that your neural network can be approximated by a kernel function, is neural tangent kernel function? So technically, once you know the kernel function, you also wouldn't need the network anymore because the kernel function has these nonlinearities sort of built in. But what I found when I looked up online, there was some pop papers, but they also explained that this apparently also helps with generalization errors, like pruning down and making it more sparse tends to actually generalize performance also, which is a nice side effect.
Can another way to view this be that we're multiplying the input by a large matrix multiplication? We're converting it into a hugely dimensional space, which then with the masking of the weights, essentially we're removing many of those points. And then we're finding the basis function, the functions that actually allow us to use that. So part of the power might be that we're producing it into such a large dimensional space that then we can find ways to segregate positive and negative classes.
Well, I think so, except that there has to be nonlinearities in the architecture because otherwise you would only be able to approximate. Like you wouldn't be able to create polynomials or Fourier basis functions because they're nonlinear.
Yep. Yes. Good to take that into consideration. So then, then you don't need to. So you take your huge matrix of random weights. You know, we do this for task 1, and then for task 2, and we really learn the masking function on that. and the which functions to use. And then for task 2, if we're going to start a new task, again, we would unmask our network, go through the learning, and then find a different mask and different weights. Yeah, so I'm really curious as to computationally how more efficient this is or not.
Yeah, I don't know if it's a lot more efficient. They do have better pruning bounds than everything else before them in terms of like, they can prove that it's faster to use their pruning methods with the proofs that they've given. One thing that I'm thinking to myself now, like, why not just use, there's this optimization method called the cross entropy method, which is like, you have a normal distribution for, like basically, is it a normal distribution? Basically, is it a normal distribution? Like, why don't we just use random search to train neural networks instead of, why do we use gradient descent? Because to me, this result suggests that, and also, why is pruning this way better than random search? And could we just use a form of random search that like does local optimization in order to, which is what the cross entropy method does, in order to find good neural networks. Because then we don't even need differentiable training objectives.
Right, yeah, why not use this completely randomized neural network and then have train the last layer with like some sparsity that makes W sparse. Wouldn't that should in principle also work.
Yeah.
Also try.
Yeah, that was the real question for me, like, do we need to use gradient descent? Like, should we just be using random search or targeted random search based on these results? I don't know. Because so much of our work is about doing things like making our functions differentiable, and if they don't need to be, then why are we doing it? It would be good to be able to talk to the author, because I feel like they would have a really good explanation for this.
Did they have a presentation? Did you pass it out?
They probably did. I'll check it out. I'm worried that it's very mathy, but because like they really care about the convergence rate and like the size of the mother network and all that kind of stuff. But
That's important.
But I'm sure
that's very important. But I have a more basic question.
Yeah.
I'm sure they worked on it so long that they have actually very good intuition of why these bounds are like they are. There's
Okay, so there's a nice project for you, Peter.
What?
Find the authors, reach out,
Mm-hmm.
and then maybe they can present a similar paper or something.
Yeah. Or just ask them, like, can we start training our models with random search? That would, because like another, I mean, they actually do say at the very beginning, like another question I had off of this was, that sparse networks are, they say over here, provided a proof of concept that sparse neural network architectures are well trainable if initialized properly. So why can't they just like train a really sparse network? Or a much small, like say you have a language model that's 10,000 or 10 million parameters, and we want one that's like 10,000. Why not just train it the same way you train the 10 million parameter model? Like what requires us to use this method of going from a larger model to a smaller one in order to find it? Like
maybe it's because gradient descent training pushes the weights, right?
Mm-hmm.
And if you have it on a smaller network, there's the chance for them to be trained in a way that actually conforms to a minimum on the whole thing is relatively lower compared to one where you spread it out, where you have many different paths where you only need one good path, right? Because eventually the other one's going to be pruned out. So I think it's really a statistical argument why it should be that way. Now, if you were to another type of hypothesis, right? If you take a sparse network to begin with, and run it as many times as you would have passed in the larger network, you probably would also with a very high chance get the same results at least one of the times. I think.
Yeah, I don't know. I came out of this one with a lot of questions, but I thought I chose it because I thought it was a very different idea than anything I've seen before. In terms of, yeah, like of finding a good model.
Do you know why it's called a lottery ticket? I think it's so odd.
Yeah, I think it should be maybe.
Because it's not luck.
I know lottery tickets exist by the middle shop.
No, I mean maybe because what they're suggesting is about luck to train a, no, I don't know.
It's
Well-
because the weights, the particular weights that you end up needing in the distilled network exist in the larger network, but just happen to all be correct, or very near to be correct. Isn't that the?
It's like a thing that every week someone wins the lottery just because so many people are playing, and here they say every time you train, there's at least one pass that is good because you have so many passes available.
Yeah.
Cool. Let's see. Is there anything else I want to point out? Yeah, I don't have anything else I wanted to talk about, but if anyone has any questions or anything that they want to mention about the paper, feel free.
Really good paper. Thank you. I've printed it off. I'll try and read it properly over the weekend.
Yeah, maybe I'll find the time too to actually go into a little bit more depth about it. I mean, going back to my point, I've actually seen people talk about using random search for training neural networks before. Anyway, cool. Thanks everyone for attending. I'm gonna close the online session. I'll stop here first. And hopefully see you online again next week. Have a good one.
All right.
Thanks.
Thank you.